Hello everyone, and welcome to the lecture on hashing. In this lecture we'll cover hashing, hash tables, hash functions, something called collision resolution, and in the next lecture we'll actually implement our own hash table class using Python. Something to keep in mind is that there's going to be a lot of topics presented throughout this lecture, so make sure you set out enough time to fully understand the topics presented here and take notes on them. Okay, so we've seen how we can improve search by knowing about structures beforehand. If you remember back to sequential search or binary search, we're able to improve our search big O by knowing if an array was already sorted when we were going to search for an object. We can actually build the data structure that can be searched in constant time, order 1. This concept is referred to as hashing. Alright. So what is hashing and what's a hash table? A hash table is a collection of items which are stored in such a way as to make it easier to find them later. Each position of the hash table, known as slots, can hold an item and is named by an integer value starting at 0. So for example, we will have a slot named 0, a slot named 1, a slot named 2, and so on. Initially, the hash table contains no items, so every slot is empty. We can implement a hash table by using a list, with each element initialized to the special Python value none. So, for example, here's a figure of what an empty hash table with size m equals 11 would look like. So we have from 0 to 10, essentially indices of our list, and they're all filled with none. So the mapping between an item and the slot where that item belongs in the hash table is called the hash function. And this is the real key to how a hash table works. The hash function will take any item in the collection and return an integer in the range of slot names, between 0 and m-1. So, what we want to think about is how should we use hash functions to map items to slots. One hash function we can use is known as the remainder method. When presented with an item, the hash function is the item divided by the table size, and this is then its slot number. Let's go ahead and see an example of how this works. So assume that we have a set of integer items, let's say 54, 26, 93, 17, 77, and 31. We've pre-assigned an empty hash table of m equals 11. That was that figure we saw earlier of just essentially an empty list. So what our remainder hash function is then, is it's a function that takes in the item and returns the item divided by 11, its remainder, so that mod function, or that mod percentage sign you can use in Python, which just returns the remainder of a division. Let's go ahead and see the results as a table. So, 54 mod 11 returns 10. 26 mod 11 returns 4. 93 mod 11 returns 5. 17, 6, 77, 0, and then 31, etc. 9. So we're doing 54 mod 11 to get the hash value, meaning 54 divided by 11 is going to be 44 remainder 10. That means we're now ready to occupy 6 out of those 11 slots, and this is referred to as the load factor, and it's sometimes denoted by this equation. The load factor is equal to the number of items divided by table size. And in this example, the load factor is 6 number of items divided by a table size of 11. That means our hash table now looks like this after it was loaded with those items. So again, we just use that hash function, in this case the remainder method, to assign slots, those number slots, to the elements or items we wanted to put into it. So for example, let's take a look here at 77. 77 was the element that we wanted to put into a specific slot in our hash table. So 77 divided by 11 is 7 with remainder 0. That remainder is the slot that we put it in. When we want to search for an item, all we have to do is simply use the hash function to compute the slot name for the item and then check the hash table to see if it's present or not. That allows the searching operation to be done at big O1, since a constant amount of time is required to compute the hash value and then index the hash table at that location. Then you might be thinking, what if you have two items that would result in the same location? We discussed about 77 mod 11 being 0, but if you had another item such as 44, that would also be the same slot number, 0. This is known as a collision, sometimes also known as a clash. We're actually going to learn how to deal with them a little later on in this lecture. What we're going to do is learn more about hash functions in general first, before we talk about collision resolution. Now let's discuss hash functions a little more formally. A hash function that maps each item into a unique slot is referred to as a perfect hash function. That means our goal is to create a hash function that minimizes the number of those collisions. It's easy to compute and evenly distributes the items in the hash table. Let's discuss a few techniques to do this. There's another hash function called the folding method. And the folding method for constructing hash functions begins by dividing the item into equal-sized pieces. The last piece may not be of equal size. These pieces are then added together to give the resulting hash function, or hash value, excuse me. So let's go through a more complicated example. Let's say our item is the phone number 436-555-4601. What we would do is take the digits and divide them into groups of 2. So 43, 65, 55, 46, and then 01. Then, after adding all these numbers together, we get 210. If we assume our hash table has 11 slots, like in the previous case, then we need to perform the extra step of dividing by 11 and keeping the remainder. That means 210 mod 11 is 1. So the phone number, 436-555-4601, then hashes to slot 1. Another hash function method is called the mid-square method. For the mid-square method, we first square the item and then extract some portion of the resulting digits. For example, if the item were 44, we would first compute 44 squared, which in this case is 1936, and then extract the middle two digits, 93, and perform the remainder step to get 93 mod 11 equals 5. Here we have a simple comparison table of various items, and then what their slot numbers would be if you use just the remainder method, or if you use something like the mid-square method. Okay, so let's discuss non-integer elements. We can also create hash functions for character-based items such as strings. The word cat can be thought of as a sequence of ordinal values. And if you're not familiar with ordinal values, in this case just think of them as a way of converting that string into numbers. You can go ahead and do a Wikipedia search for ordinal values if you want a fuller breakdown of this. But in this case, if you just want to use Python, you can actually call in the built-in function, ord, pass in this particular letter of that string, and it will give you an output of the ordinal value that relates to that string or that element of the string. In this case, passing in cat, C-A-T, will result in 99, 97, and 116, which you can then sum up to get 312, and you can perform the remainder hash function on that, and 312 mod 11 equals 4. Okay, now we've discussed hash functions in a little more detail, let's go ahead and talk about collision resolution. One method for resolving collisions looks into the hash table and tries to find another open slot to hold the item that caused the collision. So, for instance, we could start at the original hash value position and then move in a sequential manner through the slots until we encounter the first slot that is empty. This collision resolution process is referred to as open addressing, in that it tries to find the next open slot or address in the hash table. By systematically visiting each slot one at a time, we are performing an open addressing technique called linear probing. So let's take a look at an example of this. Consider the following table. Here we have 77 in slot 0 because 77 mod 11 is equal to 0. But what if we also had to add 44, 55, and 20? So with linear probing, we basically just keep moving down until we find an empty slot. meaning we've inserted 44. Instead of at 0, we moved down, checked that 1 was empty, and filled it in. 55, we tried 0. It didn't fit because it wasn't empty. Then we moved over to 1. Again, it wasn't empty, so we filled it in at 2. And we did a similar thing for 20. So, one way to deal with clustering is to skip slots, thereby more evenly distributing the items that have caused collisions. So if you notice back here, on one slide back, we'll eventually have to keep clustering things towards the beginning of our hash table. But if we want to deal with clustering, we can actually skip a certain number of slots, thereby evenly distributing those items. So the more general name for this process of looking for another slot after a collision is called rehashing. And the variation of the linear probing idea is called quadratic probing. Instead of using a constant skip value, in the last case it was just 1, we use a rehash function that increments the hash value by 1, 3, 5, 7, 9, and so on. Okay. Another note is that this means if the first hash value is h, the successive values are h plus 1, h plus 4, h plus 9, h plus 16, and so on. An alternative method for handling the collision problem is to allow each slot to hold a reference to a collection or chain of items. Chaining allows many items to exist at the same location in the hash table. Then, when collisions happen, the item is still placed in the proper slot of the hash table. So this is what chaining would look like. Instead of going around and probing for a new empty slot, you would just basically chain off the original slot. So numbers such as 44 and 55 would chain off that 0 slot number. And as more and more items hash to the same location, it should be noted that the difficulty of searching for the item in the collection increases. Alright, so we've covered a lot. We've covered hashing, hash tables, various hash functions, and collision resolution methods. Up next, we're going to implement our own hash table class. Before you check that out, I would recommend that you check out the resources section of this lecture, which has the PowerPoint and these slides we covered. Go ahead and walk through them, check with your notes, and make sure you fully understand the basics of hashing and hash tables and hash functions. Alright, thanks everyone, and I'll see you at the next lecture, Implementation of a Hash Table.